Okay, now we have a video on volumes, part 2, which is reading quiz number 7. And what we're going to investigate is what happens if we want cross-sections that are not necessarily formed from revolving around a function around the axis. All right, so with our solids revolution, our previous reading quiz, we dealt with cross-sections that were perpendicular to an axis and were circles. We don't always have to have circles. What if we did cross-sections that were maybe squares or triangles or something like that? And the answer is that when we know our formula for a cross-section, we can integrate the formula for the area of that cross-section across an appropriate interval. And our typical cross-section formula will involve integrating from a to b of f of x minus g of x all squared dx, which would indicate that we have a cross-section that's a square. So let's see an example like this. The base of a solid is the region of the xy plane bounded by the y-axis and the lines y is equal to 1 minus x, y is equal to 2x plus 5, x is equal to 0, and x is equal to 3. Each cross-section perpendicular to the x-axis is a square. Find the volume of the solid. So you'll have to bear with my attempt at a drawing here. The blue border and the red squares are supposed to be our cross-sections. It's not a very good drawing, that's why I'm hesitating on this. The better drawing is the one on the right, which comes from mathdemos.org, which gives you a better picture of this pyramidal type shape here. So how do we solve a problem like this? We need to find first the area of a representative cross-section. Well, each cross-section is a square. We remember that the area of a square is the side squared. And our trick here is to find out what a side length is. And the side length in this case is the distance between the two functions. In this case, that'll just be the difference between the two functions, 2x plus 5, and we're going to subtract 1 minus x. 2x plus 5 minus quantity 1 minus x squared will give the area of a representative cross-section. In order to find the total volume then, we just need to integrate, in this case from 0 to 3, of our example cross-section area, dx. You can see that formula on the second bullet from the bottom. We're integrating from 0 to 3 of 2x plus 5 minus 1 minus x squared dx, and our answer is 237. Notice that there is no pi involved in the answer because we have example cross-sections that are squares. The pi in the previous formula came from our cross-sections which were circles. So warning about cross-sections, they like to ask these sort of questions on the AP exam. And oftentimes they'll ask you to find volumes or set up formulas for volumes with cross-sections that are perpendicular to the y-axis. When we do so, we need to integrate in terms of y and not x, just like the previous two reading quizzes. The most recent AP volumes questions have involved cross-sections perpendicular to the y-axis, so be careful and always read the directions. Let me show you an example of that. This example is taken from the AP Calculus exam AB from 2009, question number 4. And it starts out by stating, let R be the region in the first quadrant enclosed by the graphs of y is equal to 2x, and y is equal to x squared as shown in the figure below. They say the region R is the base of a solid. For this solid, at each x, the cross-section perpendicular to the x-axis has area A of x is equal to sine of pi over 2 times x. Find the volume of the solid. Well, they've actually helped you out more than you might think initially, because the whole principle of this is that once we find the area of an example cross-section, we are able to integrate that area in order to find the total volume of our shape. Well, they've given you the formula for the area, just like we did on the previous slides here. The formula for the area was 2x plus 5 minus quantity 1 minus x squared. In this case, the area of a cross-section is just sine of pi over 2x. All right, so all we need to do to find the volume of that unusual shape is to integrate our area from 0 to 2, with 0 and 2 being the intersection points, as you can see on the diagram. All right, when we integrate our area from 0 to 2, we end up with the integral from 0 to 2 of sine of pi over 2x dx. When we find the antiderivative of this, we have to use substitution, and we get our antiderivative of negative 2 over pi cosine of pi over 2x, which we integrate from 0 to 2, and our final answer is 4 over pi. This was a calculator inactive question, so that is something that you are expected to do. Notice that the substitution would be 0 would be u is equal to pi over 2x in this case. Another solid has the same base, r. For this solid, the cross-sections perpendicular to the y-axis are squares. Write but do not evaluate an integral expression for the volume of the solid. So this is an example where you've got cross-sections perpendicular to the y-axis. So in this case, we need to write everything in terms of y. In this case, our farthest out function from the y-axis is the function y is equal to x squared. Well, writing that in terms of y, we would get x is equal to square root of y. Same thing for the line. That's our inner function, the function that's closest to the y-axis. When we rewrite that in terms of y, we get x is equal to y over 2. So the area of our square, example square, would be square root of y minus y over 2, which we then square to find the area of an example cross-section. We've now converted everything in terms of y, with the parabola part being the top part of our function. So thus, our volume would be integrating square root of y minus y over 2 squared dy. And we're going to go from 0 to 4 because those are our limits in our y direction. All right, and the question just asked us to set up an integral expression, but do not necessarily evaluate it, and so we've done so. Example 3. Find the volume of these solids that are to follow, whose base is bounded by x squared plus y squared is equal to 9, the circle with radius 3, centered at 0, 0, with the indicated cross-sections taken perpendicular to the given axis. And notice that we can rewrite our function as y is equal to plus or minus square root of 9 minus x squared, with the square root of 9 minus x squared positive part being the top half of the circle, and the negative square root of 9 minus x squared being the bottom half of our circle. So first example, we want squares perpendicular to the x-axis. So the right picture shows us the squares coming out of the x-axis, and I've tried to draw example cross-sections off here into the left picture. So the area of an example cross-section will go from the top half of the circle, the positive square root of 9 minus x squared, to the bottom half of the circle, which is the negative 9 minus x squared. When we subtract those two functions, we get 2 times square root of 9 minus x squared squared. We're dealing with squares, so that's why we square our example area. When we square that, we get 4 times 9 minus x squared. We go across the function twice, from the x-axis to the top and from the x-axis to the bottom to get our side length. So that's why we have 2 square root of 9 minus x squareds, one going to the top half and one going to the bottom half of our circle. We're going to integrate from negative 3 to 3 because that's the end x values of our circle. And when we do so, we go from negative 3 to 3, integrating 4 minus 9 minus x squared, which I just worked out right here, dx. This is a simple one that we can find the antiderivative